Good morning, Accelerated Chemistry 2 students. I hope you're having a great day so far. I'm coming to you this morning to teach you a little bit about the quantum mechanical model of the atom. And in so doing, I'm going to flip back and forth a little bit between some notes that I put together and some slides. The quantum mechanical model of the atom, ladies and gentlemen, is going to be, or can be, I should say, fairly difficult to make sense of. So we'll spend some time together in class over the course of a week or so trying to make sense of it. Today, of course, will just be an introduction. Well, let's start with where we left off. We left off with our boy Niels Bohr. There he is. And we learned in the last couple of class periods together that Niels Bohr thought electrons orbited the nucleus of an atom on these well-defined paths, right? And he also thought that you could get an electron to absorb some energy, which could take the electron from the ground state to an excited state. And then when the electron fell back down from the excited state to the ground state, you would get a photon of light produced, right? We spent some time in lab calculating those photon energies. And so hopefully that is making sense to us. Well, we now know, of course, that actually Niels Bohr was wrong. His model only worked for hydrogen. It couldn't explain some things that we saw or observed happening in atoms that are a little bit more complicated, like lithium and sodium and potassium and iron, etc. So our model of the atom, or where the electrons are around the nucleus, had to be changed. Well, a little while after Niels Bohr produced his work, a guy by the name of Werner Heisenberg came along. And Heisenberg figured out that there's no way we can know exactly where the electron is in an atom. And we call that idea today Heisenberg's uncertainty principle. It says it's impossible to know simultaneously the exact momentum and location of an electron in an atom. Now, you may not know much about momentum, but momentum deals with speed. So if we can't know the momentum of the electron, we can't know its velocity. So Werner here is saying, we don't know the speed and position at the same time for an electron. And if that's the case, then there's no way that electrons can orbit the nucleus like the planets going around the sun, all right? We know the orbit of the Earth. We know the Earth's velocity, and we know its position. And therefore, we can predict where the Earth will be in the future in its orbit. We can't do that with electrons. That's what Heisenberg's uncertainty principle says. It says we don't know the exact position and the exact velocity of an electron at any given moment in time, and therefore we can't know exactly where it is and where it is going. And so this discovery forces us to change our model of the atom. We can no longer have an atom with electrons going around a nucleus in these circular orbits. And that, ladies and gentlemen, leads us to the quantum mechanical model of the atom, okay? Quantum mechanical model starts with that idea that we can't know where an electron is, and it also starts with the idea that matter can behave like a wave. And I'm not going to get too far into the weeds on that idea right now. I'm just going to throw that out there to you, that matter has wave-like properties. Okay, if you're interested in that, you can read a little bit about wave-particle duality in your own free time. Well, the man that you see in the photograph here, his name is Erwin Schrödinger, and he uses that idea that matter can be a wave, and he uses Heisenberg's uncertainty principle, and he uses some very advanced mathematics. And instead of being able to pinpoint exactly where an electron is in an atom, what he's able to do is say that there's a certain probability that we're going to find an electron in a certain space somewhere around the nucleus, okay? So he can't tell us exactly where the electron is. He can simply calculate where we are most likely to find an electron around the nucleus. And we call those regions, those places around the nucleus where we're most likely to find an electron, we call that an atomic orbital. Now that term there, atomic orbital, is super, super important for us, folks. An atomic orbital is where we are most likely to find an electron. We might not, right? The probability of finding an electron in the atomic orbital is right around 90%. So there's still a 1 in 10 chance that the electron isn't even in that orbital and it is somewhere else. Okay? We can kind of picture what that looks like in our brain using the image that's on the screen in front of you right now. In this image, the nucleus of the atom would be at the intersection of the X, Y, and Z axes. Okay, so that means right there at the center. You might call that the origin, perhaps, in a mathematics class. And you'll notice that there's a bunch of blue dots on that diagram. Where the dots are closest together, that's the region around the nucleus where we're most likely to find an electron in this particular case. We would say that the electron dot density is high, meaning the little blue dots are close to one another. Notice, far away from the nucleus, there still are some blue dots, right? So there's still a chance that the electron is out there somewhere, but there's more space in between the blue dots. The electron density is lower, and therefore there's a lower probability of finding an electron out there far away from the nucleus. Okay, so big idea so far is Bohr's wrong. Electrons do not orbit like planets going around the sun. The best we can do is calculate the probability of where we're going to find an electron around that atom. And in so doing, we form these things called atomic orbitals. Now, if you solve Schrodinger's equations, and that requires some very advanced mathematics, what we learn is that there's more than one possible orbital. And you need to be aware of those. And so I'm going to switch views here for just a second and show you what those could look like. Let's see, I'm going to stop that little guy there. I'm going to come over here and go to my document camera. Okay, so let's draw in our notes, along with what we've already got, the different atomic orbitals that you are responsible for understanding in this class. First off, there are 4 atomic orbitals I think that you will be responsible for. They are the S, the P, the D, and the F orbitals. Those are the names we give the orbitals. It's kind of a historical thing. We're not going to get into it in too much detail right now. If you read your textbook, you might read a little blurb on it. For right now, let's not worry about why we call them S, P, D, and F. We just do. Each of these orbitals, ladies and gentlemen, has a different shape. Okay? Has a different shape. And that's what I want to focus our attention on right now. For example, an s orbital. Okay? An s orbital looks like a sphere. If there's an electron in an s orbital, that means it's likely to be in a region around the nucleus that is spherical in shape. Okay? A p orbital. And I'm going to put the word orbitals, because for p orbitals, there are actually 3 of them. They look alike one another, but they're oriented in somewhat different directions. P orbitals look kind of like dumbbells. I don't think I spelled that right there. Speaking of being dumb, that's me, right? But they look like this. They kind of look like that. It's almost like a figure 8. That's one p orbital. It can be standing kind of straight up and down. Another p orbital can be kind of lying on its side, and a third p orbital can be coming out of the paper towards your face. So I'm just going to kind of draw it at an angle like that because I have no earthly idea how to draw that three-dimensionally. If an electron is in a p orbital, it's going to be in one of these three guys that you see here. And let's just make a little note that these three guys, they always are together. And that might not make much sense to you now, but it will a little bit later on. Okay, so once again, we can find an electron in an s orbital, which kind of has the spherical shape. We could find an electron in one of these p orbitals, which look like a set of dumbbells. Okay, we can also find electrons in d orbitals, and d orbitals have far more complex shapes. I'll show you what they look like here in a second. I'm not actually going to draw them out because it's kind of difficult to do. What you need to know is that there are 5 different shapes for the d orbitals. If you need to look those up, go ahead and look at page 298 in your textbook. There's a nice diagram on that page to show you what those look like. We're never going to have to worry about drawing those in this class, okay? We should kind of be aware of what their shapes are, so take a look at that diagram, and I'll show you here in a second on a slide, but we're not going to draw them. There are also f orbitals that exist. And their shapes are even more complex than the d orbitals. So we're definitely not going to draw those. What I need you to know is that there are 7 different shapes for the f orbitals. And they're so complex, you won't even find them in your textbook. So if you want to see what they look like, ask our friend Google, and you can see what those f orbitals, excuse me, end up looking like. Okay, let me change my view here, and I'll just give you a quick little, whoops, that's not what I wanted to do. I'll give you, oh, that's Jiminy Christmas Fry. What's going on here this morning? All kinds of weird things going on. Let me show you what those look like real quickly. Those are our s orbitals there, ladies and gentlemen. You'll notice that that spherical shape kind of corresponds to that somewhat spherical electron cloud density that we see around the x and the y and the z axis. We've seen something like that before. Here are the p orbitals, once again, kind of like a set of dumbbells. And there are your d orbitals, okay? So we'll just start kind of getting used to those shapes. But I'll be honest, in this class and in pretty much all high school chemistry classes, we focus our attention on the P and the S in terms of shape. You'll see representations of the D and sometimes representations of the F, but not terribly often. Okay, let's go back to my document camera then and continue our discussion of these orbitals. And you know what I'm going to do? I'm going to tear this out because I want a little more space. So I'm just going to, I guess I should have been prepared and had this ready to go with some paper, but I'm not. Okay, we can describe in an atom where the electron is or something about the electron, its properties, using something called quantum numbers. And so I'm going to give you a quick little introduction to those quantum numbers this morning. Okay, we learned with the Bohr model that electrons can be found in energy levels, right? And the same thing is true for the quantum mechanical model. We find electrons in atomic orbitals, which are in energy levels. Okay, so if we wanted to picture that in our brain, we could do this. Let's say that this was energy level number 1. Let's just draw it like a little box, okay, just to represent it. In that first energy level, we can find an atomic orbital that looks like that. Remember the name of the atomic orbital that looks like that? If you said S, then you were correct. In energy level number 2, we can find electrons in an s orbital, Or we can find electrons in one of those p orbitals that we talked about. Okay? So electrons are found in energy levels within an atomic orbital. Now, I know that idea can be a little bit confusing. We give the energy levels numbers, quantum numbers. And for the energy level, we call it the principal quantum number. And it's represented by a lowercase n, which should look familiar to us because that's the symbol that Bohr used when he wanted to communicate energy level to someone, right? Remember the n equals 1, the n equals 2, the n equals 3. We calculate, hey, what's the change in energy in a hydrogen if the electron goes from n equals 5 to n equals 2? Same idea. The principal quantum number here, or the n, okay, indicates the energy level of the atomic orbital and its size. Okay? As the principal quantum number goes up, the energy of the orbital increases, and so does its size. Let's make a little note of that. As n increases, okay, as n increases, the energy of the orbital increases. And electrons spend more time farther from the nucleus. Farther from the nucleus. Boom, there we go. Okay? And once again, it tells us the energy level that we find that atomic orbital in. So if I say that I've got an s orbital and its principal quantum number is 2, you know that it's the s orbital right here in the second energy level. If I've got a p orbital, like this one right here I'm pointing at, and I say, hey, its principal quantum number is 3, then you know that that p orbital is in the third energy level. Okay? Moving on a little bit. Okay. Each energy level, I'm going to put n here again just to kind of remind us of that, has atomic orbitals. And I introduced that idea to you up here above with this idea here, right? The first energy level has the s, the second energy level has an s and some p's. Let's take that a little bit further and make a little chart. In the n equals 1, in that first energy level, we're going to find an s orbital. Okay? In the n equals 2 energy level, we're going to find one s orbital and the p orbitals. Remember, there are 3 of those p orbitals. In the third energy level, what do you think we're going to find? Make a quick prediction in your brain, and we'll check to see if it's right. What are we going to find? What's the pattern that you're seeing here? If you predicted, we're going to find the s, and we're going to find the p, and we're going to find the d orbitals, you are correct. How about in that fourth energy level, n equals 4? Make a prediction. What are we going to find? If you predicted S, P, D, and F, you are 100% correct. Okay? Now, one thing we need to know is that each orbital can hold 2 electrons. Okay. Huh. So in the first energy level up here, I've got an s orbital, right? How many electrons can it hold? Did you say 2? Good. So in the first energy level, you can have 2 electrons because all you have there is one s orbital. How about on the second energy level? How many electrons can there be? Well, I can put 2 electrons in the S, and I can put another 6 in the P. What do you mean you can put 6 in the P, Fred? Well, remember, p orbitals are like this. There's one p orbital, there's another p orbital, there's another p orbital. Each of these can hold 2. So 2, 4, 6, 8 electrons can be found in the second energy level. How many can we find in the third? Well, I've got 2 electrons from the S, 6 electrons from the P. How many d orbitals were there again? Did you say 5? Good. That means there can be a total of 18 electrons in the third energy level. And how about the fourth? I've got 2 here, plus another 6, that's a total of 8, plus 10, that's 18. How many f orbitals? 7. 7 f orbitals, and each one can hold 2. 7 times 2 is 14. So 14 plus 10 plus 6 plus 2 gives me 32 electrons. Okay? If I wanted to, I could do this as well. I could say that in that first energy level, I've got 1 orbital. That's the S. In the second energy level, I've got 4 orbitals, right? The S and the 3p. In the third energy level, I've got 1s, 3p, and 5d. That gives me a total of 9 orbitals. And in the fourth energy level, I have 1s, 3p, 5d, and 7 f's. That gives me a total of 16 orbitals. Okay? 16 orbitals. So there's a general rundown of the quantum mechanical model, at least in introductory fashion, quantum mechanical model of the atom. We're trying to understand, where do we find electrons? Well, we know we don't know where they are for sure. All we can say is that they're likely to be found somewhere. They're likely to be found in one of these orbitals, an S, a P, a D, or an F. Yes, the P, the D, and the F orbitals have different shapes. And there's more than one P orbital. There's 3 of them. There's more than one D orbital. There's 5 of them. There's more than one F orbital. There's 7 of them. In the first energy level, all we can have, the first energy level can only hold the S orbital. The second energy level can hold the S and all 3 of these P's. The third holds these, and the fourth can hold those. I think that's where we're going to leave the lesson for today, ladies and gentlemen. Now that you've watched the video and you've taken some notes, I need you to log into or go back to the Google Classroom for ourselves and find the introduction to the quantum mechanical model of the atom questions. And I would like you to answer those questions on a sheet of notebook paper. And when you're finished, post them to Google Classroom. They won't be too difficult, I hope. All I want to do is force you to think a little bit about these ideas that I've presented to you this morning. So far, you've sat there, you've followed along, you've taken some notes, you've thought a little bit about it, but now I want you to think in greater detail about it, okay? If it's a little confusing to you, understand that's how the quantum mechanical model is the first few times you run into it. If I see you in person during our next class period, I'll be able to help you answer questions with it. If you want some help before then, sign up in FlexiSkedge and attend my enrichment. If enrichment isn't an option for you for whatever reason, I'm always available via email. Okay? Until I see you again, ladies and gentlemen, peace.